This is DrawerSense, single camera robotic clutter clearing in constrained environments. The task for our project is, under a single mounted camera constraint, we want to open the drawer, understand its contents, and manipulate the items inside it. The setup for this project will be the KUKA Iwabot as usual, a single camera mounted on the Iwa, and a drawer containing colored boxes, as we can see here. First, we discuss the drawer opening pipeline. Since we only have a single camera that's mounted on the robot arm, we must first move towards an observation post to generate a point cloud of the scene. Then, we isolate the drawer handle. This is done by first filtering out the table from the point cloud, and then using Ransack to identify the drawer plane. This plane will be used to filter out the drawer itself from the point cloud such that only the handle remains. Then, we identify the candidate grasp. This is done by using PCA to estimate the normals of each point, and then applying some constraints to generate antipodal grasps. And we can see the constraints here. The first constraint essentially says that our two sample points must be within some distance of each other, and the second constraint enforces that the normals must point in opposite directions. And then we use compliant motion to pull the drawer open. As we can see here, we set the desired spatial velocity to some v nominal that we set if the sum of the torques is less than some other threshold on the torques that we set. Otherwise, the desired spatial velocity will be 0. This successfully encodes the resistance of the drawer into our manipulator. This is a robot manipulator setup. As we can see, it first maneuvers towards the observation post, and it also isolates the drawer's points from the point cloud. It identifies candidate grasps such that the robot can successfully grasp the drawer handle. It then uses compliant motion to fully open the drawer. And all this is done using a camera that's mounted on the robot arm.
In order to detect the objects of the scene and get a point cloud to represent them, we consider two different approaches based on vision loads. One of them is based on sound and clip, so we apply fast sound on the RGB image and get the clip embeddings of the segments. And then we compute the causation similarity of those segments with the clip embeddings of text labels that represent the objects that could be on the image on the scene. So then we aggregate the masked point clouds resulting from those segments over multiple views. There's two ways we can do that robustly. So one of them is applying cosine similarity threshold per each view and then concocting the point clouds that represent each object. The other one is computing the cosine similarity average for each point and for each object. So then we can threshold the points based on how likely they are to be in that object over multiple views. And the third one is applying Bayesian inference based on a probability distribution that represents how likely a point is to be on an object given the cosine similarity. And then we can have a better idea of um, which points are in which object. Uh, the other approach is using SUM3, which allows us to prompt the segmentation based on the text prompt, which is the labels that we have. And then we can get better segments and just like aggregate them over multiple views the same way as before. In general, it seems like SUM3 performs better for multiple objects in the same scene. However, there's trade-offs between the performance of different approaches given various conditions like occlusions of objects.
The next step after getting the point cloud from the perception system is to pick the object up. We sample many antipodal grasping based on the point cloud and choose the one that is collision-free. Then the manipulator will follow the trajectory, pick up the objects, and place it on top of the drawer. We also use a state machine to coordinate other subsystems. There are totally 4 states. The state of handle plane estimation uses Ransack to find a feasible handle grasping, and the drawer extension state using the combined motion to open the drawer. The segmentation state using SAM and clip to find the best target grasping poses. And the last state, pick and place, choose the best antipodal grasping and move the target on top of the drawer. Each state will only advance to the next state if the requirement is satisfied. Here's our demonstration of the perception and grasping pipeline. The target here is the yellow box. As shown in the video, our pipeline successfully segment out the yellow box from the rest of the color boxes and find the best antipodal grasping, manage to move the box to the top of the drawer.